This is video 2 of topic 7 on hydrological simulation models. In this video, we'll talk about watershed modeling. Hydrological models can divide or discretize watersheds in a lumped, semi-distributed, or fully distributed fashion and may simulate hydrological processes using physically based mass and energy conservation equations, analytical expressions that simplify these conservation equations, empirical equations, or a combination of these approaches. We learned about this in the previous video. Some models have the capability to address specific hydrological processes in great detail, while others may lack the necessary hydrological process representation. Models also differ in data and resource requirements, ranging from relatively simple procedures that can be applied in a matter of days to highly complex models that may take several weeks or months to set up and calibrate. In fact, there are many different hydrological models available, and very few new model development is currently supported. So what's done typically is to use the existing models and possibly to modify them slightly, rather than developing entirely new models. Engineers must therefore choose among the existing models based on the characteristics of the system under study, the objectives that they're trying to meet, and the available budget for data collection and analysis. So here's a handy table that's showing some of the differences between a low complexity model, a medium complexity model, and a high complexity model in terms of data requirements, resource requirements, and time requirements. And so as an example, if we're dealing with a low complexity model, we only need monthly precipitation and temperature data. We don't need any additional meteorological forcings. We don't need maps. We have fewer than 25 different parameters to deal with. And the parameters can be experimentally based, so there's no calibration even. And then the models are suitable for ungauged basins. On the opposite side, with high complexity models, we may need hourly or daily precipitation and temperature data. We may need additional meteorological forcings. We might require very sophisticated mapping data, so digital elevation maps, soils, and forest cover. There are often 75 or more parameters that need to be set up, and then a medium to high number of calibration parameters, and it can take weeks to months to calibrate one of these models. And these models are applicable for gauged basins only. In terms of resource requirements, low data pre-processing efforts, they don't require GIS analysis, and it can be completed by one person. For the high complexity models, there's a lot of pre-processing that has to be done. GIS analysis is required for most of them, and it may actually require a project team. And this last one gives you a much clearer idea of how much work is actually involved. For time requirements, for a low complexity model, maybe less than 2 weeks and you have your analysis done. And it can be done for about $10,000 or less. Whereas on the opposite side, it could take 2 to 6 months to prepare your model, and it could take between $40,000 and $100,000 to actually get this work done. So you can see it does matter what you choose. In terms of watershed modeling steps then, the model selection is a difficult and an important decision, as you saw from the previous slide. The success of a project can hinge on the accuracy of your results. And so unless you have digital watershed data that are extensive in space and time, the usual approach is to use a deterministic event model with lumped parameters for developing hydrographs and flood routing. HEC-HMS is used widely for a typical watershed analysis to convert rainfall into runoff and stream flow, and we're going to focus on HEC-HMS in video 3 of this topic. For a watershed with extensive rainfall, infiltration, base flow, stream flow, and soils and land use data, you can use HSPF from the US EPA Basins model. This can calculate continuous long-term water balances and outflow hydrographs. It is a much more detailed model than HEC-HMS. And then for a well-defined urban drainage network, a distributed event-based model like SWIM, the stormwater management model, can be applied. Here you'll define the hydrological response for different components throughout the system. Bedian presents this set of watershed modeling steps. The first is to select the model based on the study objectives and the watershed characteristics, the availability of data, and the project budget. The next step is to obtain all necessary input data, the rainfall data, the digital topography, land use and soils, infiltration channel characteristics, stream flow data, design floods, and reservoir data. Then to evaluate and refine the study objectives in terms of the simulations you need to perform under various watershed conditions. Step 4 is choose methods for determining the sub-basin hydrographs. So unit hydrographs, SCS, Clark, Snyder, various others, as well as different channel routing mechanisms. Okay, then number 5 is to calibrate the model using historical rainfall, stream flow, and existing watershed conditions, and then validate your model using other events under different conditions while maintaining some calibration parameters. The 6th step, after we've done all of this, is to perform the actual model simulations using historical or design rainfall, various conditions of land use, and various control schemes for the reservoirs, channels, or diversions to the extent possible. Number 7 is to figure out how sensitive your model results are to the various parameters that you've used. So here you'll perform sensitivity analysis on input rainfall, routing parameters, and hydrograph parameters as necessary. So you want to see how variable your results are based on your assumptions. And then finally, you're going to evaluate the usefulness of the model and comment on needed changes or modifications. So remember earlier I said there are no new models being developed. The models that exist are always being modified and upgraded and maintained and so on. And so evaluating the model performance is very useful for those steps of improving the model. It's worth talking about that 5th step a little bit more. That was the calibration and validation step. This is a really critical component because it determines how useful, reliable, believable your model results are. And so for calibrating, our idea here is to adjust or fit the model parameters to produce accurate results for the next steps of that procedure. We're going to select a set of measured input data and measured output hydrographs, and then we adjust the controlling parameters until we get the best fit we can obtain for the set of data that we used. This is what it can look like. Here's my gauge record in blue, and here are the obtained simulation results in red. And you can see they don't line up perfectly. We don't expect them to because a model is a simplification of reality. And so whatever processes that gave rise to this blue peak here may not actually be included in my model. And so I'm looking for the best fit, but not a perfect fit. Here's another example of the same. So you can see here the observed values are these square values or square markers, and the simulation is the smoother blue curve and the smoother red versus this marked path here in red. To validate then, we simulate a second or a third event in our calibrated model using different inputs. We keep all of the other parameters unchanged, and then we compare the predicted and measured hydrographs from our different input values. Here's an example of how calibration can really change your model results. This is a study done by a former PhD student of mine. Here you can see the results that were simulated for an uncalibrated model, and here are the gauge records that we were trying to match. We then spent some time calibrating the model, and you can see how much the results improved. They're still not a perfect match, but they're a much better match. This took about 3 months of effort to go from here to here. Let's talk about some of the different models that are available as well. The table here shows some of the most popular event, continuous, and urban runoff models for hydrological simulation. These are developed by different universities and federal agencies around the world, many of them in the United States. Many of these are well documented and have been used really widely. Others have only been used in a few specific locations. And so the one we'll learn in this course is HEC-HMS. You'd learn HEC-RAS in some of the water resources engineering courses. SCS-TR20 is a bit like HEC-HMS. HSPF you've heard about previously. SWIM is the stormwater management model. I've also talked about that briefly. And Mike Urban and Mike Flood come from the Danish Hydraulics Institute. And so these are quite widely used as well. I believe these two have been folded now into the HEC-RAS model. The dates here are a little bit deceptive. As far as I know, all of these models are still regularly updated, and so the date could actually be 2020 for all of them. The next slides then review several of the surface water models in this table. I'm going to leave you to read the details on your own, but I will talk very briefly about each model here. So HSPF is the model of choice for evaluation of continuous runoff and non-point source loads. This is an older model, and it's the commercial successor of the Stanford watershed model. It's available from the US EPA. This is the overall structure of the HSPF model. You can compare this to other figures of the hydrological cycle you've seen throughout the course, and you'll see that it's quite a close match. ISBA top model is another widely used hydrological model. This is developed in France, and so it's the Interaction Sol-Biosphère-Atmosphère model. You can read more about it here. EPA's SWIM model is the most comprehensive urban runoff model, and it provides for continuous or event simulation for a variety of catchments, conveyance, storage, treatment, and receiving streams. Both water quantity and quality can be simulated. This is, again, a very widely used model. The Danish Hydraulic Institute has developed a fairly large number of different models, all called MIC. These address engineering problems of rainfall runoff, pipe flows, overland flows, water quality, and sediment transport. And so here's a little bit of information on Mike Urban. Here's a bit on Mike Shee. This is what the user interface looks like for some of these models. And this is what you can actually do with the models. So here's another set of simulation results. You can see they can be quite sophisticated outputs. And then Mike Flood is suitable for handling flood assessments, flood hazard mapping, flood risk analysis, and integrated urban drainage design. But again, there's a large number of models available. This is only a selected subset. This ends video 2.